Assalamu alaikum everyone. In today's video we will be discussing topics, and we will initially start from discussing the representation of numbers. Though in last class in last video actually we did introduce some topics. Once again I want to start from there. What the first thing comes here is the representation of number, and here I say that dependent on something called the words. Okay, by saying that representation of numbers are dependent on words, I actually now need to explain what words are. So here we are given a very one word answer, which is words are a number of beats. So the number of beats is a word. That means if we want to express it, for example, if I have 3 beats, I can express 0 1 2. Sorry, if I have 3 bits, I can actually express from 0 to 7. If I have 2 bits, I can express from 0 to 3. What I'm trying to say is that if I am given a permission to express number using suppose 2 bits, let's write it down a little bit. So if I'm given the permission to represent numbers using 2 bits, I can use 2 bits. Suppose one is a bit 0, and I call the other one such as bit 1. Then I can represent 0 by writing 0 0. I can represent 1 by writing 0 1. I can represent 2 by writing 1 0, and finally I can express 3 by writing 1 1. So if I'm given a word size of 2, then I actually have 2 bits to work with, and then I can express numbers starting from 0 to 1 2 and 3. So okay, I think I still need to change the page number. So here we are once again back. Dependent on words, the representation of numbers is dependent on words, and words are the number of bits. The more bits we have, the larger numbers we can express with it. But word size varies from machine to machine. Each type of machine, each different machine has a fixed length for word, that is how many bits it is going to provide for me to help my calculations. Now these are 3 simple words, that is computers use binary numbers, humans understand decimal number very easily because it's used 10 digits, and hexadecimals expresses more in less digits because it has the maximum number of digits among the number systems that we are talking about. It has 16 digits. So these are the first few parts, and then we have the integer representation. Now the fact is, the integer representation says for word size n, the maximum possible number is 2 to the power n, among which one example I saw that I showed earlier, that if we use 2 bits, that is 2 to the power 2 squared, that is 4 minus 1 3. So we did see that, and same goes for all cases. Now there is another topic here, that negative numbers stored as 2's complements, that is the negative of a number needs to be stored, then it is actually converted to the 2's complement and stored. Well, it can vary a bit depending once again from architecture to architecture, but this is these are some common features to keep in mind while working with integer representation. But however, our main objective here will be the floating point representation. So to start off with floating point representation, I think first I would like to show you some examples. For example, you are given a number, say, oh, sorry, once again. Okay. So suppose that you are given the number 12.67. You are given 0.15, you are given 101.5, or you are even given 0.002. These are all example of floating point numbers, right? But as you can see that these are very different representations, but when we want to work with a computer, we have to have very specific and fixed way for representing these numbers. Hence comes the floating point representation, which is expressed over here. All numbers are expressed in a single type of format. All numbers are converted to this format, which is given here, that if any number is given in any format, it will be converted into f into 10 to the power minus e format. So how is it like? If I want to show an example, it will be more or less like this, that the 12.67, which is a number, well, we can change the value, that's for sure. We have to ensure that the value remains unchanged. So what we can do is we can convert it into 0.1267. Now we can easily see that there are two numbers over here. It was 12.67, so clearly this 0.1267 is achieved by dividing this whole number using 100. So what will we do? We will multiply this number 0.1267, we will make it 10 square. So now the number we have over here, which is 0.1267 into 10 square, it is actually similar to the number given over here. Similarly, for 0.15, we can write the same 0.15 into 10 to the power 0. The value remains unchanged. For 101.5, we can say that we can convert it into 0.10. I guess this one will not make some sense. Let's see, 0.1015. Now you see I have shifted it 3 digits in the right, so I'm going to multiply it by 3. Essentially the number remains unchanged, and over here we have a different situation. The given number is already in fraction and nothing is in the left. Even in this case, we need to convert it into a format that is useful to us, so we will convert it into 0.2. Now I have converted, I have actually shifted the number to the left, so 2 steps to the left, so I have to multiply it using 10 to the power minus 2. The value remains unchanged. You must be careful about that. The value needs to remain unchanged, but all these numbers over here are actually in this format, f into 10 to the power minus e, and we do need to convert everything into this format. Why? In this case, we have f as the one called mantissa and e as the one called the exponent, and thus what we can say over here, that we can now convert the whole memory into 3 specific parts only. We will call one part mantissa, the other part will be called exponent, and the remaining bit will be the sign bit. So now if you watch it carefully, you will see that all the 3 parts of our example were given. They can be represented as integer numbers now, and thus this is how a floating point number can be stored in a computer. Over here is given an example that in a typical 32 word environment, we can expect a 24 bits to be mantissa, 7 bits to be exponent, and a single bit for the sign. And here is a visual representation of such case. Well, if we just consider the previous scenario where we wrote an example of suppose the example of let's say 0.15 into 10 to the power 3. If we can express it like this, we can easily say that, okay, let's give it a minus as well. So this is a minus. So we can easily say that in the sign bit, for suppose for my minus we store 1. Suppose for 15 we may store the binary number of the 15 in 7 bits. The 15 will be 1 2 3 4, and 1 2 3 4. The other bits will be 0. I believe this is the binary representation of 15. 8 4 2, so 6, yeah, pretty much. And remaining the sorry, this is the exponent part, my bad. So we can express it using 1 2 3 4 5 6 7, and thus goes on. In total there will be 24 bits. And in the exponent part, as we have 3, we can store 1 over here and complete the other bits using 0 or so. Now we actually have the binary representation of this number, or a floating point number, in the computer. So thus this is how a number can be stored in the PC. A floating point number can be stored in a PC based on its architecture. So this is how floating point numbers are stored. Our token of advice: this is not the only mechanism to store the floating point number. Some take a number before the decimal point, some take a number after decimal point. There are what you call standards. I'm showing one standard. It is not the only standard available. There are other standards as well, and you are free to use any acceptable standard. I will not be enforcing the standard I show here as the final standard. So you are free to check out other standards as well and take the one that you think is suitable to you. So the standard we are trying to follow over here, in this case, when a number is given, we first shift the number using the decimal points. What we want is a non-zero value to be present after the decimal point, and no non-zero value to be present before the decimal point. Okay, suppose we always want a number which is not 0 to be present after decimal, and before the decimal point we want all values to be 0. This is the standard I am following, but once again, just as I said, there are other standards as well. You can follow them. So first of all, we need to shift the numbers, as we saw the examples before. So the shifting of decimal points, this is normally called normalization, and a number which has gone through the normalization process is called a normalized floating point number. Now you see, these are normalized floating point numbers, as you saw, and they can be expressed like this or this. Both are acceptable representation. Now what we need to remember, that this is what I just said. The conditions for mantissa is f mantissa needs to be less or equal to 0.1, greater or equal to 0.1 and less than 1.0. And another condition is it has to be greater or equal to minus 0.1 and greater than minus 1. And if you combine these two conditions, we can write it in a single line like this. So next up is computer arithmetic. Okay, here we have given a small talk about integer arithmetic, which will not be much of a discuss in this part. Well, always what we need to remember, that integer arithmetic says that all the results must be in integer. That is, even if you divide 7 by maybe 3, the answer will be 2, not 2 point something something. No, it's not accepted. The answer will be just 2. This is integer division, that we do not care about what happens after the decimal point. And in such cases, sometimes formulas can be false. For example, we can see a by c plus b by c equals to a plus b by c. It is actually a formula. You can say that we take the c common and a and b are plus, but it's not the case. For example, we say if a equals to 1, b equals to 1, and c equals to 2. Now if we consider integer division, this part, a by c will equal to 0, b by c will equal to 0, and summing these two up will still equal to 0, but a plus b divide by 2, if we do that, divide by c, we do that, it will be 1 plus 1 divided by 2, which will ultimately result in 1. So you can see that the left hand side and right hand side are do not matching, though this is actually a correctly written mathematical form. So this is said when we say, so this is what we mean when we say that for integer operations some formula can be false, because we are actually forgetting about some parts of the math over here. So let's move on to our main topic, which is floating point arithmetic. Floating point arithmetic, and first up is addition. Okay, so what we need to know, that first there will be two numbers that will be given. Suppose one number will be x and the other number will be y. One number will be x and the other number will be y. Okay, so x will have two parts. First, when we convert it into, we will say f of x and e of x. Similarly, y will have two parts. We will say it's f of y and we will call this e of y, and there is the result which will be expressed as z. It will be called f of z and e of z. So these are the three parts that are said over here. Now comes the calculation part. Okay, so for the sake of this example, I am considering that I am already given the numbers in floating point arithmetic itself. So it might not always be the case. You need to first convert it into an acceptable floating point representation. But for this example, while I'm doing it, I will consider the floating point representation is provided. Once again, please look at your question before answering. So I will say that one number is 0.264 into 10 to the power, say, 2, and another number is 0.521 into 10 to the power 1. Suppose these are the two numbers that are given, so we can say the actual numbers are actually 26.4 and 5.21. For our sake, let us first see what is the answer. So we can say that the actual answer is 31.61, but this is not the mechanism we will want to do. This is just a part we are keeping, so we know that our math is working fine, right? So let's get started. Over here, the rule is provided that you first need to find the larger number. So over here, how can you find the larger number? It's easily visible that based on the power value. So first we will look at the power value. We can see that this power value is higher, so we know that this is the higher number. Where if the power values are same, then we look at the number itself. From there we can assume the comparison of which one is larger. So over here we can see the power numbers are different, so easily we can say that this number is larger than this number, so this is the larger number. And by finding this out, you have to make the exponents of the number equal. So over here we have 1, but over here we have 2, so we need to make it equal. So we need to make this number change so that this is become 2, and in such cases we will have to convert 0.521 into 0.0521 into 10 square. This is how we convert it. Now this new power is found, and now that both powers are same, what we say that the add mantissa. Okay, let's add the mantisses over here. So now we have let's write it down, 0.264 and 0.05 Some of you may think, why are we making this complex situation not easy sum? But unfortunately, this is how computers store the numbers, and hence we have to follow that in order to learn how the computer works. So please bear it with me. So 0.3161, and as you can see, all the powers over here are 2. So this is our fz, which is 0.3161, and we have an ez, which will equal to as all the other numbers are 2, this will also become 2. If somehow our sum resulted in something like 3.3161 or so, in that case we would need to normalize it once again, that is convert it into once again a floating point representation. So here's an example of addition. Please take your time, pause the video, or have a practice yourself. Next up is the subtraction. All the systems are same, just the difference is subtract the mantissa rather than adding it. And in the next part we have floating point arithmetic of multiplication. This is a little different once again, so let's have another example about it. So once again we take the previous two examples, 0.264 and 0.521, I think that's what I remember. This one was given 10 to the power 2, and this was given 10 to the power 1. Now what will happen over here? It's straight cut, multiply the mantissa, add the exponents. Okay, let's see what happens if we multiply these two mantissa. Let's calculate it out. So if we try to calculate it, if we calculate 0.264 with 0.521, the answer is by multiplying these two, the answer we get is supposedly 0.137544, and then it says that add the exponents. So over here the exponents is 2 and 1, so we can say that the exponent will be 10 to the power 3. So this is the number we got after the part, and once again we have to normalize if necessary. Hence this is the number that it will be result, and in reality if we multiply 26.4 with 5.21, we get 137.544, which is actually same, because by 3 we will have 3 powers on the left, and hence this is actually the same value we will find. So this is the floating point arithmetic of multiplication, and next we have the division, which once again actually does the same thing, but the exponents are subtracted and the mantissa are divided. Next topic is error in arithmetic. Okay, one thing we must remember, that points after decimal may induce errors. That is, if I find that suppose after an experiment the result is 1.229164523. Suppose I found an experiment result as this, but as there are too much numbers after the decimal point, I want to truncate it. I want to say that the number is 1.2292. Okay, well, till the decimal fourth point I can say the answer is right, but actually when I write this, it actually means the remaining values are all 0 until the infinite. So I'm actually trying to say over here that I have consciously or unconsciously have induced an error. For example, over here it will be quite a large value. Over here is 7 7 4 4 sorry 5 3 error like this value. So this is an error that will be found, that this is the amount of error because I did a truncation. So this is what the points after decimal may induce errors because we are might as well as truncate it in several cases. And even if you want to keep all the values, we can do it, because keeping too much values may induce underflow and overflow problem in later cases. uh, so, so when we actually truncate these values, it causes another problem. It violates the law of arithmetic because sometimes we are forgetting some important parts. So this is a trade-off that we must always work with, either how much error we want to take in exchange of how many values we want to forget for easier calculation. So it cannot be avoided, it needs to be done. So this is important, and because we have to make a trade-off, sometimes we take in that we accept that we will be facing some errors. Now, how is error calculated? Over here we have said that error, if represented E, it is actually the difference between the true value of x and the approximate value of x. Now in this case, negative numbers are possible, but we just want to know how much we deviated from the real answer, and in that case we calculate the absolute error instead, which is the difference modulo, that is only the absolute value. But absolute error may always not work with much, and hence in many cases we work with relative error when we see or work in numerical methods. And in honest opinion, it is actually very common to use relative error in order to understand how well or how bad the situation is working, because absolute errors can be of huge value, but relative error in that sense, view actually is capable of giving a more accurate understanding of how good or bad an error is. For example, if I say that my real value is 5 and my approximated value is 4, then relative error will say that the difference is 1, but absolute error will say 1, but the relative error will say 5 minus 4 divided by 5, which is 1/5. Okay, then for an absolute error it will say, suppose 100 minus 99. The absolute error will once again say that the error is 1, but look here, we only worked with small values, but now we are working with larger values. 199 is not very small, but absolute error still says it's the same. But what will happen if we say the error is 100 minus 99 divided by 100? As you can see that the weight of the error is reduced by a lot much, and it is actually very practical. When we are working with small values, we want it to be more accurate in the smaller region, but when we are working with large values, we actually can consider a little, okay, it's okay, we can consider this much. The consideration range actually increases in real life. So in that case, relative errors are actually more practical to work with. Now there's a part says error propagation. So what is error propagation? If I want to express the, suppose that error propagation is something like this. Suppose the true value of x, which is expressed as xt, is actually I don't know, maybe 2, and I have approximated that x's value, x approximation is 1.9. Okay, now I write a function that says f of x equals x cube minus 1. So this is my function. Now the value of f of xt and let's see what will be the value of f of xa. So as it is an x cube minus 1, we can say the value of xt should be 7, but as xa is 1.9, the result will be 5.859 if I'm correct. Now over here the error was only of 0.1 deviation, if I want to say the absolute error. But what about this? Because I only took a 0.1 error, the error over here actually increased to a great value, right? It's not anymore 0.1, this is 7, this is 5, so almost it's 2, I can say approximately 2. So this is what error propagation is. If you keep error in a lower stage, the higher the stages go, the more it gets faulty. This is the concept of error propagation. Now error propagation, as I mentioned earlier, we have to take errors, but we also want the result to be as accurate as possible. So in such case we try to calculate condition number. Condition number is a concept which states that the lower the number of condition, the less sensitive the system is to the change of the value, the less the system is vulnerable to the error. This is what the condition number states, and there is no fixed measurement. It is just something that is calculated to understand how much sensitive it is. So over here the condition number calculation formula is given. You may want to remember it for your exam, and the lesser the condition number, the more stable the system is. It is less prone to error propagation, so we can say that we can give it more age when we are trying to consider whether or not to work with it. So this is all. Oh, and one more thing, if the condition number gets very large, it is usually called ill conditioned, and when anything is given ill conditioned, what we want to say is take more numbers after decimal points, because it is more prone to errors. So that is it for today's video. Thank you very much everyone. See you in the next class.